Thanks for the invitation from CFIA. It's a great honor to participate in today's Congress. I'm He Jing, an architect from China, working at China Institute of Building Standard Design and Research, and serving as observer for Committee on Engineering and the Environment of Warfield. Today, I'm very glad to have the opportunity to share the topic of building and climate change with you. As an architect, my understanding of professional responsibility has improved with the development of time. When I was a college student, I had been deeply fascinated by formal beauty. After a few years, in the context of the global energy crisis, I realized that energy saving needs to be prioritized over formal beauty. For example, large glass curtain wall may look cool, but it may cause excessive use of air conditioning and lights, whether in winter or summer. Recent years, the increase in extreme weather events remind us that the premise of building design is no longer static. In the context of global climate change, mitigation and adaptation may become important responsibility of architects. Architectural history has lasted for 1,000 years. The relationship between buildings and climate shifts from responding to climate to adapting to and mitigating climate change. Before the 20th century, the structure, shape, depth of floor plan, and even decoration of buildings were actively responding to climate to keep warm, cool, and light. Architects of the time made the most of wind and sun without artificial lighting and air conditioning. For example, Chinese courtyards can provide shade, cooling, and daylighting. These courtyards are also shaped differently from North China to the south to accommodate different sun altitude angles. Wind catcher in North Africa and West Asia harness the cool breezes and redirect them downwards into the home or underground rooms. Large eaves of the roof and colonnade both can cool the interior in summer. Pantheon in Rome only set a circular window in the center of the dome, but it can direct natural light to the floor. These climate-responsive designs also contribute to the diversity of architectural cultures, while providing comfortable living spaces. And since the 20th century, with the using of concrete, lighting, air conditioning, building design can no longer be constrained by climate. Electric lighting and mechanical ventilation allow light and air flow to every corner of any shape of building. Air conditioning can create the same indoor temperature, regardless of different outdoor temperatures. The use of these energy-using devices leads to direct and indirect carbon emissions. At the same time, reinforced concrete structures have greatly improved the power of construction. Its construction speed and height are far more than masonry structure and wood structure. Landmarks at that time were probably as tall as a modest office building today. The production of cement and steel used to make reinforced concrete emits large amounts of carbon dioxide. Cement, in particular, produces carbon dioxide from fuel burning and chemical reactions. Technological processes also lead to culture conversions. Today, some new urban areas around the world seem to look the same. However, the old parts of the cities have a great diversity of architectural culture. Technological breakthroughs are like a coin with two sides. With population growth and urbanization, the 20th century saw the largest number of buildings built in history. Building industry in the century consumes the largest amount of non-renewable resources, emits the largest amount of greenhouse gases, and make the most important contribution to global climate change. In 2020, building sector accounted for about 37% of global carbon emissions. Building operation accounted for about 27%, including direct and indirect emissions from lighting, heating, and cooling. Construction emissions accounted for about 10%, mainly from embodied carbon emissions, that is, emissions from the production of building material such as cement, steel, and glass. The increase in greenhouse gases causes global warming. According to the newly IPCC report, global warming of 1.5 degrees Celsius and 2 degrees Celsius will be exceeded during the 21st century unless deep reductions in carbon dioxide and other greenhouse gas emissions occur in the coming decades. That means more buildings will be exposed to long summers and even heat waves. Research shows that by 2050, 1.6 billion urban dwellers around the world will be regularly exposed to extreme high temperature. Rising temperatures will put pressure on the building and its occupants. At a high temperature, construction workers may not be able to work outdoors due to the fatigue and illness. And rising temperatures will decrease heating demand and increase cooling demand for buildings and affect outdoor thermal formal. And the thawing of permafrost caused by temperature rise may damage the stability of roadbed, cause uneven settlement of the roadbed. And extreme temperature can also reduce the efficiency of solar photovoltaics. And it's not just temperature. Climate change will also increase the frequency and intensity of extreme weather events such as hurricanes, floods, droughts, and wildfires. This will increase the pressure on human survival, as well as losses of built assets. A study shows that under the global temperature rise, floods in China will become more frequent than before. And a combination of economic and climatic factors, flood losses will be 4 to 17 times higher than in historic times. And global warming will also cause sea level rise. Research shows that more than 516 cities will be vulnerable to sea level rise and coastal flooding by 2050. Rising sea level can result in inundation of buildings and infrastructures in low-level regions. And the rise of underground water level caused by sea level rise may cause the failure of anti-floating design of basement, partial structural damage, or even the whole structure floating. Buildings that can last for decades or even hundreds of years will be challenged by climate change throughout their lifetime. It can be said that building activities are both involved in and affected by climate change. Today, building engineers face the new responsibilities. How to mitigate the contribution of building activities to climate change, and how to increase the adaptive capacity of building to future changing climate. This is a double challenge. Mitigation includes reducing embodied emissions and operational emissions of buildings. Regardless of the reduction of operational emissions or embodied emissions, there is the same strategic logical, that is, reduction of excessive consumption, technological process, new energy and materials substitution work together. IEA outlined a series of milestones for the global building industry to achieve net zero emissions by 2050. This path is a combination of multiple strategies. And then some cases. The roof of a recently completed high-speed railway station in China is entirely photovoltaic. The photovoltaics can reduce carbon emission by 4,500 tons per year. And the photovoltaics panels sparkle like ripples of water, reflecting the local water culture. A nursing home in Spain has adopted passive housing technology to maximize the thermal preservation, insulation, and airtightness of building envelope, and to reduce heating and cooling requirements by recovering heat from indoor exhausts through the heat recovery unit of the fresh air system. Combined with solar photovoltaics, the building could generate more energy than it consumes. Shape design of a building will determine its later energy consumption level. Buildings with natural ventilation and lighting can effectively reduce the use time of air conditioning and lights. In the future scenario of global warming, it is more important to consider the architectural form. Because simply relying on more air conditioning to cool homes during hot summers will increase energy consumption and emissions, which could further exacerbate climate change. This vicious circle needs to be avoided. Designing buildings that can be naturally ventilated and even cooled is a positive preparation for the future. It plays both adaptation and mitigation roles. And moreover, shape of a building cannot be changed once it is built. Unlike doors, windows, and air conditioners that can be replaced. Therefore, form design is the first level of low-carbon design. Some nature-based solutions can lead to more natural ventilation and light and increase resilience of buildings, addressing to hotter summers in the future. The latest UN report, A Practical Guide to Climate-Resilient Buildings and Communities, provides lots of useful strategies. And some creative designs help cool down and gain heat naturally. An office building in UK designed a series of chimneys with ventilation to cool the office below. People can turn off the air conditioner and open their windows to the yard to let the breeze into their offices. Farmers in northeast China are also smart. They installed vegetable greenhouse in front of their houses as sunrooms to warm the indoors during the cold winter. The cost of the plastic shed is extremely low, and the temperature inside can reach 25 degrees Celsius to 30 degrees Celsius, creating a comfortable space for the family. And after winter, the shed is removed to prevent overheating in summer, and it can be reused in the next winter. Till now, new structural materials that can universally replace cement and steel has not yet emerged. That is to say, cement and steel will continue to be the main materials for building construction for some time. But that doesn't mean there is nothing we can do. We can find ways to reduce the overuse of materials. For example, extending the life of building can reduce the overuse of cement and steel during a longer period of time. The strategies may include improve the adaptability of functional transformation of building space to avoid repeated demolition and construction, and improve the durability of the main structure, and strengthen the detection and maintenance in the use stage, and improve the resilience of buildings to future disaster risks. The use of prefabricated decoration can reduce the amount of cement used in wet work, especially floor leveling, because studies show that the cement consumption in decoration can meet a third of that in main structures in a 50 years life building, because it can be done more than once. And the modular toilet in the prefabricated decoration can not only reduce cement consumption, but also facilitate pipeline maintenance and replacement. Using wood and bamboo can minimize embodied emissions of the buildings. Wood differs from most every other building materials in that its production only emits a small amount of carbon and can act as a carbon sink. An 18-story tall wooden structure has been completed in Norway. Its beams, columns, and even elevator shafts are made of wood. To mitigate climate change, the project used all local tree species. And an eco-restore in Bali has been constructed using bamboo founded directly on the site, so the restore become completely carbon zero. Adaptation efforts are also required because buildings are often designed based on the climate experience of past few decades. There may be a gap between the existing adaptive capacity and required adaptive capacity and the climate change scenario. Therefore, the concept of resilience needs to be integrated into the traditional design to bridge the gap between today and the future. Building scientists and climate scientists are collaborating to develop future climate design data and corresponding climate resilience strategies. This will trigger a shift in the way of building design. For example, the 2025 version of the Canada National Building Code will consider new climate change provisions. And some cities, such as New York City, have developed design guidelines for dealing with future climate risks. Facing a changing future, engineers are exploring some creative resilience strategies. For example, a multi-purpose hall in Bangladesh is built on some pillars. The pillars can be raised by buoyancy tanks below and allow the hall to act as an emergency shelter during floods. A rehabilitation hospital in US adopts resilience strategies such as raising the ground floor, placing the equipment on the top floor, redundant energy, and passive survival design to resist and adapt to climate change risks such as flood and sea level rise. In 2015, Warfield published the Code of Practice on Principles of Climate Change Adaptation for Engineers. This model code of practice provides further amplification and explanation to engineers and national engineering organizations to interpret and implement principles of climate change adaptation at a practical level. It consists of 9 principles that constitute the scope of professional practice for engineers to initiate climate change adaptation actions, particularly for civil infrastructure and buildings. And in 2021, Warfield launched a new project, Climate Change Mitigation Best Practice Project. It will build a database platform to collect, organize, and store successful engineering projects, plans, and ideas from Warfield national members and partners. The changing relationship between building and climate is a cyclical process of exploration, just like the human cognitive process. The challenge of climate change will also be an opportunity for design and technological innovation in building industry, for we can shape a more resilient future. Thank you.